Hi there, welcome to another college mathematics video. In this video, we'll continue looking at geometry. In particular, we'll start to see closed figures. We'll get lots of names and definitions for them so that we can ultimately get to that hands-on, more interactive stuff towards the end. Okay, so our objectives for this video: look at vocab for polygons, find angle measures, find measures of size in similar figures and congruent figures, and find measures of polygon angles. Some notes to start us off. Like I said, we're going to start to look at closed figures now. So the first definition we have is the general for pretty much everything we're looking at throughout this section. The first is a polygon. This is a closed figure in a plane made of 3 or more lines. Remember from the previous video, a plane is a flat two-dimensional surface, so we're still in 2 dimensions. It's a closed figure, 3 or more lines. Those lines could be the same, they don't have to be. Could be 20 lines connecting in some sort of crazy looking shape. It could very simply just be shapes that you're familiar with. But the polygon is general for everything. Then more specifically, we have a regular polygon, in which case all sides have the same length and interior angles have the same measure. So this would be your special figures like the triangle where all 3 are the same, the square, because that means all 4 are the same. 5-sided. I'm not going to give away the name yet because that'll be one of our notes later. The next thing we have are similar figures. These are where corresponding angles have the same measure and lengths are in proportion. Similar figures is sort of like having, let's just say the example is a triangle, and then zooming in on that triangle. They have the same angle measures. Nothing changes about the general feel for the shape. It's just, are you zoomed in or are you zoomed out? How close to the shape are you? I did not do a great job drawing them to look quite so similar, but imagine that they were zoomed in, zoomed out version of each other. And so if this is the case, let's say we labeled the 3 sides to be A, B, and C. It's pretty common to see A, we would say prime. It's not a 1, it's not an exponent, it's just a notation. B prime and C prime. This indicates that these are the matching sides. A matches with A prime, B with B prime, C with C prime. And if that's the case, then we know that the angle measures are the same between the 2 pictures, but the lengths of their sides are in proportion. So what do proportions look like? A goes with A prime. B matches up with B prime, and C matches up with C prime. So you wouldn't necessarily use this entire formula all the time. Most likely you would cut one of them out. Let's say you have some information for A and C, and then also for A prime and B prime, and you were trying to figure out the other pieces. You would just use whichever portion of the equation you had 3 pieces for. And we'll see some examples later. And then the last would be congruent figures. These are where corresponding angles and sides have the same measure. So we're looking at 2 shapes still, but these aren't necessarily a zoom in or zoom out. They're the same copy and paste shape, figure, whatever it is you're looking at. Imagine you were trying to create the same bulletin board all over campus. You would want to cut this one this size, and then the same here and the same here because they're all the same. Let's say we had a 4-sided figure. We'll go A, B, C, D. They should be the same. Pardon my imperfection here on drawing them. And then they could be labeled however. It's actually common to see both used here. So just because you see the tick mark used in one way or another doesn't necessarily mean that, oh, this is definitely similar figures, or oh, definitely congruent figures. You will be told they're similar or they're congruent and then go from there. And if they're congruent, then there's no really even algebra in any sense to solve. If they're congruent, they're the same. A is the same as A prime, B is the same as B prime, C is the same as C prime, D the same as D prime. So if we knew information for one figure and not the other, we could easily figure it out because they're the same. We should be able to figure that out with no problem. All right, a few more notes. The next thing we'll look at are the names of polygons. I think we'll go red here. So these are all the different sides that would be in the figure, and we're going to fill in what the corresponding name would be. So if we have a three-sided figure, this is polygon, which means the three or in whatever number, the sides don't have to be the same length at all. So a three-sided figure is a triangle. Easy enough. How about a four-sided figure? If you said square, not exactly. A square would be one of them that falls under this category, but square is a very specific type of this thing. And also it wouldn't be rectangle. In both of those cases, there are some sides that have to be the same, equal to each other for it to work. But a general four-sided figure, polygon, the four, one could be this long, one could be this long, one this long, one this long, connect them in any way. A four-sided figure is a quadrilateral. We'll take a deeper look at specifics with triangles and quadrilaterals later in the video. The rest we're just getting the names for. A five-sided figure, general five-sided figure, is a pentagon. A six-sided figure is a hexagon. A seven-sided figure is a heptagon. An eight-sided figure, you can probably get this one, an octagon. Nine-sided figure, nonagon. A 10-sided figure, a decagon. We skip 11 to go to 12. A 12-sided figure, a dodecagon. And then a 20-sided figure, these are the only ones with special names, an isosagon. So remember, these are general polygons. The sides may or may not be the same length in the figures. If they were the same length, then we would have a regular triangle, a regular quadrilateral, regular pentagon, regular hexagon, and so on down the list. All right, a few more notes. Now we're going to start to look at triangles in a little bit greater detail. Remember in the last video we talked about different types of angle measures that exist. We can classify all triangles in two ways. The first way has to do with their angles. Remember we listed the special types of angles, one of them being a right angle. Well, we have a right triangle. Could be shifted any way, but what will be true about a right triangle is that it has one right angle. The other two ways we could classify a triangle based on its angles. We could have an obtuse triangle. In an obtuse triangle, we have one obtuse angle. And then the last way we can qualify a triangle based on its angles would be an acute triangle. Acute, something like this, connecting. Now it's probably tempting to say this one will have one acute angle, but that's not the case because a right angle also has an acute, it has two. An obtuse angle has two acute angles. An acute triangle has all three. All acute angles. If we say just one, technically it could end up being one of the others. All right, so this is if we're classifying the triangle only according to its angles. We could also classify triangles according to their sides and angles. I'm sure once I say one of them, the others will come back to you. The first way we can identify a triangle based on sides and angles is isosceles. Oops. Isosceles. An isosceles triangle has at least two sides and two angles equal. Could have isosceles. We could have an equilateral triangle. An equilateral triangle, I would say the most special, has all three sides and angles equal. So equilateral, all three are the same. Isosceles, at least two. And then the third one is if none of them are the same. And this would be called a scalene triangle. My example, definitely not perfect. It has no sides and no angles. Equal. So every triangle can be classified in one way and the other way. Any triangle, you could look at it and say it's obtuse, right, or acute. And you could also say if it's isosceles, equilateral, or scalene. Just different ways you could identify them based on solely angles or sides and angles. Okay, and this takes us to one of our other objectives, which is finding the sum of the measures of interior angles of regular polygons. The objective is simply finding individual angles. So this is one of the few formulas we'll have here, and I just want to highlight this word, regular polygons. Remember, we had a definition in the beginning for polygon and for regular polygon. This formula that I'm about to list only works if it's a regular polygon. It's a very simple formula. N minus 2 times 180. This is the formula for the sum of the measures of interior angles. So imagine you have, now it has to be regular, so I'm sorry that it's not a regular looking shape, but let's say this is a shape we have. You have a whole bunch of angles in here. The sum of all those angles is a certain number. You can find that number, the sum of all those angles, using this formula if it's a regular polygon. N minus 2 times 180. The only thing you need to know is n. And n is just the number of sides in the figure. So again, you can only use this on regular polygons. And you'll know how many sides there are because you can count them or you'll be told. Plug it in, subtract 2, multiply by 180. Pretty easy. There's two types of questions you could see with a problem like this. So let's go ahead and do them up top here. The first one would be, let's say we have this picture. I'm going to try to draw it so that they're all the same. My intention is that this is a regular polygon. You'll be told. Regular polygon. Okay, you could be asked sum of the measures of the interior angles. If that's the case, plug into the formula. How many sides does this figure have? 1, 2, 3, 4, 5, 6. 6 minus 2 times 180. Looks like we get 720. This would give us the sum of the measures of the interior angle. So all of these angles added up together would be 720. The other question you could be asked is what's the measure of one interior angle? How do you think we find that? Well, if we know that the sum of the angles is 720 and there are 6 angles, just divide. 720 divided by 6 gives us 120. So this angle right here, 120. All the rest 120. I don't quite have enough space to fill them all in. You could be asked either question. So in this case, I asked both, but you could totally have the first piece, what's the sum? That question could totally be gone. They could just say, what's the measure of one interior angle? The truth is, you have no choice but to first find the sum and then divide by however many sides there are to get this answer. But that's about it. That's really the only variation you'll see in a problem like that. Okay, so we looked at triangles in greater detail. Now let's look at the special quadrilaterals, more quadrilaterals in detail. We've got quite a few, as you can see, 2 slides to fill in. The first one is a trapezoid. So we're going to draw the picture and then write why it's special. The only thing that's unique, it's still a quadrilateral, but it's special. I'll use these arrows to indicate that the sides are parallel. So the only thing special about a trapezoid is that it has 2 parallel sides. The next one we look at is a parallelogram. In a parallelogram, what makes it special is both opposite sides are parallel. And both opposite sides are equal. I'd say the bigger one is that they're parallel. Parallelogram, top parallel, top bottom parallel, left right parallel. And then just by default, since they're parallel, it's going to make each of the side lengths equal to each other. Top and bottom, left and right. I'll use the arrows for parallel, and then we use tick marks to indicate equality. Okay, the next figure we look at is a rhombus. A little bit more special. My drawing is not great. In a rhombus, both opposite sides are parallel. And all 4 sides are equal. So imagine quadrilateral as the umbrella for any 4-sided figure. Underneath that, you've got, hey, this could be a trapezoid because it has 2 parallel sides. Could also be more specifically called a parallelogram. Any parallelogram could also be called a trapezoid because it meets the criteria of having 2 parallel sides. So sometimes quadrilaterals will fit more than one of the specials that we're listing here. In those cases, just go with the one that has the most criteria. Or I suppose you could write both. That's not a big deal. So again, a rhombus could also be called a parallelogram because both opposite sides are parallel and equal. It just so happens that all 4 are equal. What we're going on the next page, the last 2 are your rectangle and square. And I just want you to look at parallelogram and rhombus. It's a parallelogram is sort of like a rectangle that was the top and bottom were pulled sideways. And a rhombus is a square that was shifted sideways. Those we know. Rectangle. Lots of criteria. You know what it looks like though. Here we go. Criteria to be a rectangle. Both opposite sides parallel. And both opposite sides equal. This was the criteria for even a parallelogram. So what's the additional thing that makes this special are these right angles. And all 4 angles right. They're right angles. Remember that means they're 90-degree angles. So it's a parallelogram that's been shifted and stood back up straight. And then the last of the special quadrilaterals we look at is a square. Lots of criteria again. Again, we have both opposite sides parallel. And all four sides equal. Same criteria as rhombus. The additional thing that makes this special, all four angles are right. Which again means they're 90 degrees. So lots of different classifications that we've looked at. Let's do a little practice with these. All right, so it's on 2 slides, so if you need to copy or pause the video to copy these down, go ahead. These are going to be the choices for the questions on the next page. Whoa, that one's not showing up at all. I'll draw that one in there. The one that is difficult to see here. Letter D, sorry, it didn't show up. A, B, and C are just the angle names, A, B, C. And then each side is 5 centimeters. So these are your options. Again, if you can't see this one, man, these all say 3, 4, 4. I think those are visible. This is 5, 5, and 3, 9, 10, 2, 6, and those are not listed. Okay, so these are the ones you're using to answer the questions on the following slide. Here they are. Which are regular polygons? Which kind of polygon is B? You can read through them. Go ahead, pause the video, answer these questions, and then let's see if we're on the same page. Okay, so I have the pictures to reference for myself since I don't want to go back and forth. Which of these are regular polygons? Remember, regular means all the side lengths are the same in the shape. And for our pictures, we had letter A because each side was 3, 3, 3, and letter D because each side was 5, 5, 5. Everything else there was some variation in, so couldn't be considered regular. Oh, and letter B. So we have top, left, right. Yep, let's make sure it's the same. Yep, good. And letter B. Perfect. Okay, what kind of polygon is B? Polygon general, how many sides does it have? That's your first name, and then can you be any more specific? So the type of polygon it is a quadrilateral because it has 4 sides. Can you be more specific? Now that we know it's a quadrilateral, can we go any further in describing it? And we can. We know it's a rhombus because all 4 sides are equal, opposite sides. We don't necessarily see the note that the top and bottom and left and right are parallel, but if top and bottom, left and right are the same, it's going to be the case. And it's a rhombus. A square pulled sideways since all of the sides are 4. You might be wondering, well, I see a 2 on the right-hand side of letter B. That's telling you the height. It isn't telling you that side crooked length. Okay? The third one, which are similar figures. Similar figures, a zoomed in, zoomed out version. So the angles are the same, but the side lengths are proportional. The only place we have that is A and D. And you would have to have said both of them. Because we have 3, 3, 3, and then 5, 5, 5. It's just zoomed in and zoomed out. Which of these is or are an isosceles triangle or triangles? Letter A definitely is. Why is A isosceles? Remember, the definition for isosceles says at least 2 sides and angles equal. It definitely has at least 2. In fact, it has all 3. So A. Letter C definitely is. We have 2 sides, 2 angles, and then letter D also for the same reason as A. Which of these are equilateral triangles? Equilateral means all 3 are the same. That's A and D. What's the name of figure E? How many sides does it have? It doesn't say regular, so it's just how many sides. We count 6, so it's a hexagon. And that's the last question that deals with the pictures we saw on the other slide. We have a couple more practice problems. And these are to deal with a couple other things that we need some kind of algebraic work on. So find missing sides and angles, and then the measure of one interior angle of the regular polygon. Quick note before you pause the video, you'll see, for example, here between A and B on the left, it looks like it's a comma, and it is a comma written there, because in many other countries, they flip-flop in math the use of a period and a comma. So this is 9.4. Obviously, the picture came from another country because they are writing with a comma. So where you're seeing comma, it's decimal. It's meant to be a decimal. So go ahead, pause the video, use the formulas you saw at the beginning and in the middle to answer these questions. We'll see if we're on the same page. Okay, so let's see if you got the right answers. Missing sides and angles of the similar triangles. Now it looks like these are the same, but you were told that they're similar, so you know that they don't match up equally. They match up in proportion. Okay, so let's start with angles. For me, angles is a little bit easier. The angles, let's do red just in case. The angles inside a triangle have to add up to be what? If you didn't remember, you could use the formula that we had on the other page. The angles in a triangle add up to be 180. So if we have 80 plus 35 here, we can figure out the third angle to be 65. 180 minus 80 is 100, minus 35 is 65. You could also figure it out by looking and remembering that similar triangles have equal angles. So these match up. This is 65, these are 80, which means this one over here is 35. You'll have to use both ways of doing it sometimes. So that's one thing, missing angles, done. The other thing is missing sides. You might be tempted to use Pythagorean, but we don't have a right triangle. We'll see that later, but you can't use that here. It doesn't work because it's not a right triangle. So the only thing we can do, since we know they're similar, is use those proportions. Now, you just have to pick which one you want to be on top, which one you want to be on bottom. This is the larger of the two triangles because these measures are bigger than these measures. So I'm going to compare small to large. You can go large to small, it doesn't matter. The only known proportion, because these two match up, these match up, and these match up, the only known proportion is 8 and 16, so we have to use that. The small has 8, and the large has 16. Then we just have to pick which one do you want to solve for. Let's start with y. So these two go together. The small has 5.5, and the large has y. This is the equation we're solving. Writing small over large is no longer of any use. It's just this equation right here that we worry about solving. So you can cross multiply. Cross multiply. 16 times 5.5. Darn, no calculator. 8y, all right, I'll do it by hand. 30. Again, 3. 8. It's one decimal, 88. Divide by 8, y equals 11. Good. 11. So there's one missing side. We need another missing side. You might also have recognized, especially between 8 and 16, that this is a really nice, clean relationship. 8 to 16 is times 2. So going small to large is just times 2. Going large to small, divided by 2. And that definitely works. 5.5 times 2 gives you 11. Going the other way, divided by 2. Back to 5.5 definitely also works. So you could do the same process that we just did for this piece, or you can recognize that relationship and use it. I'm going to stick with the method I just used because not every relationship is so clean. Times 2 divided by 2, that's a nice one. It doesn't always work out that nice. So I'm going to go ahead and keep doing it this way. All right, so my known proportion is still 8 over 16. That's the small to the large. And then the one I'm looking for is in the small, so x is on top, 9.4 on the bottom. Cross multiply, I have 16x equals 9.4 times 8, 75.2. And then divide by 16. X equals 4.7. Something seems wrong there. Let's see. Small to large, 16x. Seems good. Yeah, okay, 4.7. Perfect. All right, so that gives us the two missing sides. And this is the strategy that you'll pretty much have to use for those problems. Angles, hopefully, is easy. You just kind of match them up and then use the fact that they add up to 180. Sides, you've got to use these proportions. If we were told they're congruent triangles, it would, for the sides, be just as easy to just match them up. That's a simple one. That's why we did similar as a practice problem. Okay, then the measure of one interior angle of this regular polygon. The question is simply one interior angle. So we don't necessarily care about the sum of the measures, but we really have no choice other than to find it first. So remember the formula is n minus 2 times 180. Our n, in this case, we have 8 sides, and we are told that it's a regular polygon, so we can do this. 6 times 180 is 1080. And then we only care about one angle, so divide by the number of sides we have, which is 8, and we get 135. So the measure of each of these is 135 degrees, one interior angle. All right, so this video we started to look at the closed figures a little bit more. Got a lot of definitions and a lot of ways to classify triangles and quadrilaterals in particular, and then looked at comparing similar and congruent figures. Our examples stayed primarily with triangles, but the idea with similar and congruent would work with other shapes as well, as long as you were told that it was similar or congruent. So in the next video, we'll start to look at more stuff with those closed figures area in particular. I'll see you soon for another video.